Welcome everyone to the second of two press conferences at the 56th annual meeting of the Division for Planetary Sciences of the American Astronomical Society, that we just call it DPS. I'm the press officer of the DPS, Dr. Teddy Kareta, and I'm joined by my colleagues from the AAS, Dr. Susanna Kohler and Dr. Carrie Hensley. We have three really exciting presentations for you today that have a shared theme in some ways and are also uniquely interesting, and I think you're going to get a lot out of them. Before we get started, I have a few remarks to make. The first I'd like to say is that if you're in Florida or you're going to be affected by the hurricane, maybe a lot of scientists traveled for the Clipper meeting, maybe you're at the science meeting itself. I hope you're staying safe, and I hope that you're able to keep your friends and your colleagues safe too. I have a few comments about how these press conferences work, but the first thing I'd like to emphasize is that these three scientists have taken time out of their meeting here in Boise or online and virtual to talk about their science to you. That takes time, effort, and they're losing a lunch break, the worst thing in the world. They have colleagues they've talked to, they have colleagues that they've brought with them today here to help answer questions. This is a lot of effort, and they're making it so that you, the public, you journalists, can understand it better. It's a really cool opportunity, and you should be thankful, I know I am, for all the hard work they've done about it. We're going to have each of them give each of their presentations in order. Amy, then Richard, then Mariah. And afterwards, we'll do Q&A. If you're watching live on Zoom right now, you can enter your questions throughout the talks in the Zoom Q&A box, and we will answer them verbally afterwards for the benefit of people watching online later. We're going to try to ask questions of each presenter approximately equally, and we hope that all of your questions reflect the respect that you should have for these people who've taken their time out of their busy weeks for you, right? Regardless of what kind of institution they're at, what kind of career stage they're at, they're doing this for you. And I think that's a tremendous service. The DPS does tons and tons and tons of cool research. And what you're going to see here today is just a subset of it. So I'd encourage you that if you're seeing this for the first time, go back and watch the first press conference, or, get exposed to all the cool things the DPS is doing. Let me see if there's anything else I have to mention. One thing I'll mention briefly is that after this is publicized and put online, contact information for the presenters will be made available. And if you have any particular questions you're dying to ask or you didn't quite get answered on the Zoom call, you can still do so, even if you're watching this days, weeks, maybe not years later, but, in the future. Susanna or Carrie, is there anything else that I missed before we can get started?
I don't believe so.
Awesome. So with that, I'd like to invite our first speaker, Amy Simon, to share her screen, and everyone else who is on the call, you can turn off your videos and microphones, and then we can get rolling.
Okay. Thank you. I'm going to be talking today about oscillations that we observed within Jupiter's Great Red Spot. And this is a long-term study that we've been hoping to do, and we were able to just complete it this year. So first of all, we have what's called the 90-day oscillation. And if you don't live and breathe the Great Red Spot, you probably don't think about that much. So what does that mean? And what it means is that, first of all, the Great Red Spot is drifting westward with respect to the planetary rotation. But it doesn't do so at a constant rate. So it oscillates with a 90-day period where sometimes it's moving a little bit faster, sometimes it's moving a little slower. And we've seen this in the historical database. We've seen this in ground-based data. So that was a well-known phenomenon. In addition to that, some other large anticyclones, for example, Neptune's Great Dark Spot, also oscillated in longitude, but at the same time, it oscillated in latitude, and it also sort of sloshed around. So it oscillated in its tilt as well. And using those parameters, it was approximately in balance. The Great Red Spot, we didn't see those sort of latitude and tilt oscillations, but it was still thought to be in balance, at least during the Voyager days. But we now know that it's much smaller than it was then. So we wanted to see if anything has changed and also to look at this in more detail. So we used the Hubble Space Telescope to study the Great Red Spot over a full 90-day period from December 10th to March 8th. And we measured all of its different characteristics: its latitude, its longitude, its size, its shape, its color, and its interior velocities. And we did this with a variety of filters. And so if you look at our plot here, this is where the Great Red Spot was sitting during each of those dates that we observed. And sometimes it was ahead of where it should be if it were moving at a constant rate, and sometimes it was behind it. In addition to that, if you picked a set point and looked at what its drift rate was over that time, looking back to that point, you can see that clear sinusoid. So our overall goal of this program was to better understand atmospheric structure within the Great Red Spot and be able to feed this into future circulation modeling. So this is the data that we had. We had 6 separate filters. We had a UV filter, which is sensitive to stratospheric haze. We also had color filters, so violet, green, and red. And the red filter we also used for wind mapping. And then we had 2 filters that are called methane gas absorption filters that are sensitive to the highest clouds and haze in the troposphere. So for each of our dates, we had repeated image pairs, often with 10-hour separations and sometimes also with 1 hour, that we were able to use that red filter to map out the wind field. In addition to that, we had to name a bunch of these features that we were consistently looking at the same thing. Next to the Great Red Spot, we have what's called the wake, which is a convective area, and we also have streamers, which are these high altitude areas that are flowing into the Great Red Spot. In terms of the features I'll talk about, we have what's called the red ellipse, and that's the edge that we see in that green filter because that's kind of the sharpest one where we can see that contrast. So that's a continuous ellipse. And then we have the core, which is the dark central region. And so those are the 2 areas that we distinguish between when we're looking at size. And then we have the color, that's that area in between that we also use for color. Now, the reason we did these different filters in different colors is because they tell us different things about the atmosphere. So we can do a red, green, blue image, which is what you're familiar with seeing with your eyes. And you can see even on 2 different dates here, the Great Red Spot looks quite a bit different between those two dates in color. But some of the real information comes when we look at altitude. And so we can use those UV and methane gas filters and distinguish which things are at higher altitude. And so this middle version here has the methane filters in a specific order, and it really brings out those high features. It tends to be brighter and a little bit pinker in those high altitude clouds. If you flip the filters around, you get more sensitivity to the deep features, and you can see very deep clouds as red in that image. So to look at the oscillation, the first thing we did was we had to set the phase of the oscillation. So we looked at each image we took and found the center of the Great Red Spot by measuring where the core was in longitude and also looking at the velocity field and seeing where the center of that was. When you do that from date to date, it sets the drift rate. And from that, we get our oscillation. So you can see that it was kind of moving at the slowest in the middle of our observations. And then we can plot each of our parameters and see if they fit a 90-day oscillation. And so we didn't assume going in that anything would have a 90-day oscillation, but once we confirmed we had one, we went ahead and let it vary to see where it best fit the data, if at all. And what we found was that the size of the Great Red Spot, that red ellipse, particularly in semi-major axis, so width and longitude, does oscillate over 90 days. We found that the north-south dimension didn't actually oscillate, though. But when we looked at the core, both its height and its width oscillated also with 90 days. And they're all about the same phase, approximately correlated with when you see it in the drift rate. We also looked at color, and each map was converted to what's called I over F, or reflectance. So basically, how much of the incoming sunlight do you reflect back out? And we looked at both the core and that color region in a bunch of different filters. And what we found was that the core oscillates in the UV. It's a small oscillation, but it does get brighter over that 90 days. And the color also has an oscillation, but it's out of phase with the others. And we see that in the violet wavelength, so where it's got the most blue absorption. So we are seeing some color oscillations over 90 days as well. Lastly, we looked at velocity fields, and we used an automated technique that iterates back and forth between those image pairs with 10-hour separations and shorter ones when we have it. And you generate these nice wind fields where you can see all these little vectors that tie to those clouds. When we map that out in velocity space, we can fit an ellipse to that high velocity region, or we can look at the average velocities basically on spokes coming out of the Great Red Spot. And we do both ways because sometimes you don't get a nice continuous ellipse. And here on December 10th, you can see we had really good fits. On December 28th, on the other hand, we didn't, and we had a region where it really did not fit well along that ellipse, and that's why we also do that spoke method. And so if we plot out the velocities that we see, those maximum velocities with both of those methods, we don't see any evidence of an oscillation, even though there's some variation, but there's also very big error bars. And so what we found was that we're not seeing any oscillation in those velocity fields. But back when I was talking at the beginning about this balance, what we would expect is that if it were a very simple structure, following some simple approximations, we should have seen the velocity basically oscillating with those other parameters because that's what's helping it to balance out. And so what this is telling us is that those simple models, which really kind of assume the Great Red Spot is 2D, don't work. So we're seeing as we have a much more complex structure than really a simple model allows. So what we have here is a movie. It's an animation that's showing all those oscillations at the same time, correctly in the phase that we measured. The colors are a little bit exaggerated, but the size and motions are exactly matching what we measured. And so we saw oscillations in the drift rate, in the size of that outer red ellipse of the red spot, in the core itself, and also in the colors. And we also found that some of those parameters were very much correlated with each other. So the Great Red Spot is its biggest. It has its largest width when it's moving its slowest. And we also see that that's when the core is the brightest. The only variation that we saw that was out of phase was that color, so the redness essentially around the edge of the Great Red Spot. And with that, I will stop.
Okay, great. Thanks so much, Amy. I'll mention two things before we move on. Is that first, Amy is thankfully brought some of her colleagues with her today. So for those of you asking questions in the Q&A box on Zoom, afterwards, we have a bunch of people in the room who are total experts on this sort of thing. Will be really helpful. Secondarily, I'll mention that Amy's home institution has prepared a press release for this, which we'll distribute as well with more resources. So with that, I will invite Richard to turn on his video and get ready to start sharing the screen. From Jupiter, we're going to jump and skip past Saturn and head straight to Uranus, and also change which space telescope we're talking about. So Richard, take it away.
All right, thank you, Teddy. I'm delighted to have an opportunity today to present JWST data on the Uranian moon Ariel. And also, a quick heads up, at the end of this presentation, I'm going to present currently unpublished data for Umbriel, Titania, and Oberon as well, collected with JWST. So I want to start with a little bit of background on what Ariel is, what do we know. That image on the left is the best imagery that we have collected by Voyager 2 in 1986 during a brief flyby of the Uranus system, achieving about 1 kilometer per pixel at best for Ariel. And it exhibits a relatively young surface, a lot of evidence for tectonism and potential evidence for cryovolcanism as well, which we're going to get into in a little bit. But Voyager 2 was not equipped with a near-infrared mapping spectrometer, so everything we know about its surface composition comes from ground and space-based telescopes. As great as those data sets are, and I'm going to present some of them today, all of them are disk integrated. So we don't have spatial information. We don't know what the composition of different geological units look like on this moon. And we're not going to know that unless we send a mission back to Uranus, the currently envisioned UOP, the Uranus Orbiter and Probe. So then getting into the results. So to start with, Ariel's surface it's an icy satellite. It's primarily made out of water ice, but its surface is also mantled by a large amount of CO2 ice, as well as we think with a minor amount of carbon monoxide. Now, the key for these carbon oxides are that at Ariel's peak surface temperatures, they're mobile, they're volatile, they're going to sublimate, they're going to leave the system via Jeans escape. And so they have to be replenished by some mechanism over geologic timescales. One way to do this is through irradiation, because Ariel is in Uranus's magnetosphere. Charged particles in that magnetosphere could interact with Ariel's surface, interacting with water ice mixed with carbonaceous material and generate CO2 molecules in situ through a process called radiolysis. Or the CO2 could actually be native to this moon and is being slowly outgassed over time from its interior. Now, in this endogenic scenario, the CO2 could actually originate in a subsurface ocean that then is outgassed to the surface. And an interesting wrinkle in this, along with the CO2, is the possibility for carbonates, so CO3-bearing salts, which are hard to make on the surface of airless bodies. And so if we see evidence, spectral evidence for carbonates, most likely they have to be made in a liquid layer that's in contact with rock, and then those salts slowly precipitate out over time and then get expressed at the surface through one geologic mechanism or another. And then the key take home here from the JWST results, they seem to better support a geologic origin for carbon oxides on Ariel. It's important to note, we're certainly not ruling out the irradiation hypothesis. It's certainly possible that irradiation is playing a role. It almost certainly does to some extent, but we're increasingly coming around to the idea that carbon oxides might primarily originate, at least in the interior of Ariel. So then going back to its geology, as I mentioned, it has a relatively young surface, perhaps about 1 billion years or so, with some pretty chunky error bars. 1 billion years is pretty young for solar system objects. And in fact, the regions that have been age dated are not most likely the youngest that are on Ariel. Using cross-cutting relationships, we know that there are features that were termed the medial grooves, which is what that white arrow is pointing to in the yellow box, that cross everything else. And so they must be the youngest unit from a geologic perspective because they're on top of everything else. But we don't know how old they are because we can't get good crater counting statistics because the data is just not good enough. And so even though Ariel has a young surface, statistically, it may even have a younger surface than we're able to appropriately measure. Okay, so getting to the JWST results, again, these are all disk integrated data. We don't have spatially resolved information in terms of surface composition. That blue image on the right there, that's an image sliced showing you Ariel as it was imaged or collected a spectral cube with JWST about a year ago. These are the best ground-based data we have of Ariel, showing clear evidence for water ice, as well as narrow and weak features associated with CO2 ice and perhaps carbon monoxide as well a little bit. And then we have data at longer wavelengths from the ground too, between 3 and 4 microns, and you can see those data are terrible. It's really hard to observe icy satellites at longer wavelengths. The atmosphere is out to get you. It's absorbing all your photons, and water ice also absorbs very strongly at these longer wavelengths, and the data are pretty bad. But the real power of JWST, by being above Earth's atmosphere, it can collect really great data between 3 and 5 microns. And then so with an hour of exposure time on Ariel, we can see an absolutely dramatic improvement in the signal to noise and just really beautiful data. Now, between 4 and 5 microns, we don't even have ground-based data at all. And this is where JWST can really do some heavy lifting. And because we know there's CO2 ice on this moon based on the shorter wavelength features I was pointing out earlier, which are weak, then we would expect a really strong 4.3 micron band, which is one of the strongest CO2 features that can hypothetically be detected, but we can't see it from the ground because CO2 gas in our atmosphere completely blocks it. So expected to see a big honking CO2 band. So of course, instead we see a giant peak. So now zooming into those data showing the leading and trailing sides for Ariel. Again, clear evidence for CO2 ice. Those are peaks or scattering peaks. They're not emission features. And what we think is happening is there's a layer of CO2 on the surface of Ariel. It's somewhat porous. Photons are able to get in there and scatter around and then come back to the observer, and you get these large scattering peaks in extremely basic terms. We confirm the presence of carbon monoxide, and I'm going to talk more about that and its spectral properties in a little bit. And then this longer wavelength feature, which is also associated with CO2 ice, which I point out because you don't see this feature unless you have a thick layer of CO2. It's from collective oscillations across a crystalline CO2 lattice. It's not a traditional vibrational mode. So if you see that, you've got a lot of CO2. And then also tentatively some possible spectral evidence for a broad 4 micron band associated, we think, with carbonates. And going back to what I said earlier, if we're seeing carbonates on the surface of this satellite, then it's pretty good evidence that at least the carbonates, if not the other carbon oxides, originated in its interior. This is a busy plot, and I'm going to move through it quickly. The take home here is we see some subtle features associated with CO2 ice on the surface of Ariel that shouldn't be there unless we have thick, concentrated deposits that are segregated at least from water, if not from other components. And the existence of this thick layer is, again, consistent with a geologic origin. In terms of the thickness, it's about 1 centimeter, but that's all we can measure using photon penetration depths. It certainly could be thicker than that in some locations. Then taking a closer look at the CO feature, which is zoom in here, comparing it to some laboratory data, it's not consistent with pure CO ice at all. It has these pretty big side bands, which are likely associated with CO mixed with CO2, and then CO mixed with water, perhaps even CO clathrates. So this is where you have a CO molecule trapped in a crystalline structure, which would be, if we confirm that, would be compelling evidence for an endogenic origin as well, because clathrates are really hard to make. You generally need high pressure environments. And so if we see it expressed at the surface, it likely formed in the interior and then got exposed by hook or by crook. We also look for hydrogen peroxide. This is H2O2. This is an interesting compound. We see this feature on Europa, on Ganymede, on Enceladus, and on Charon from recent results. And it's generally made through irradiation of water ice. Well, Ariel has a lot of water ice, and it orbits within Uranus's magnetosphere. And so it was logical to think that we might see H2O2. And the take home is, I know there's some text here about some other features, but the take home is we don't see any evidence for hydrogen peroxide at all. And this is interesting. It could mean that there's so much CO2 in Ariel that the charged particles essentially get gobbled up by the CO2, and they're unable to efficiently interact with the water ice underneath. And in that case, maybe that's why we don't see H2O2. Otherwise, perhaps the irradiation environment is actually somewhat quiescent at Ariel's orbit, and instead, this would support an endogenic origin for carbon oxides if, in fact, the radiation environment is quiescent. So then finally, from my perspective, Ariel is an ocean world, and a more relevant question is, where does it fit on the spectrum of ocean worlds between something that's generally considered to be dead, like the main belt asteroid series, which has bright carbonate-rich deposits on its surface, and then all the way to the hyperactive Enceladus, which has plumes that are jetting material into space, which is mostly water vapor and water ice, but also CO and CO2 gas. And it's likely that Ariel falls somewhere in between these two end members. Okay, as I said, I was going to show spectra for the other moons. Here again are those data for Ariel. The carbon monoxide feature that we confirmed is shown in blue font. We haven't seen this feature on any of the other moons. And I'm happy to say that we do see a carbon monoxide feature. It's much weaker than what we see on Ariel, and it's on at least one of the hemispheres for the other moons as well. And all the carbon oxide features we see on the other satellites are significantly weaker than Ariel. Thank you.
Okay, great. Thanks so much, Richard. I think that was really interesting. It's always so funny when planetary scientists will talk about 90 days in one talk and then a billion years as a short period in the next. It's the best field ever. So with that, I will invite Mariah to get started sharing her screen. So we skipped Saturn, and now we're going to skip Neptune, and we're also going to skip the rest of the solar system and jump straight to exoplanets. And Mariah is going to talk to us about how the exoplanetary systems we see might be structured. Take it away.
Yes, hello everyone. I'm super excited to be participating in this. My name is Mariah Jones. I go to Vassar College, and I'm going to be talking about my summer research project I did at the SETI Institute, which involved investigating the stability of Trojan and Horseshoe co-orbitals and extrasolar multi-planet systems. So firstly, what is a co-orbital configuration? They consist of two or more bodies sharing the same orbit around a host, and these bodies are what are known as co-orbitals. Now, I'll be talking specifically about two types: Trojans, which Trojans which are particles that share their host's orbit, and they liberate about the stable Lagrangian points L4 and L5 with an angular separation of 60 degrees. And also horseshoes, which have much more complex paths, and they are 180 degrees apart in longitude. And now these two specific types of configurations are found within our solar system. However, only 3 planets host stable Trojans, which are Mars, Jupiter, and Neptune. Now, what is the cause for this instability in Saturn and Uranus? Well, it's due to their near resonances with Jupiter and Neptune, respectively. And Saturn specifically is in near 5-to-2 ratio with Jupiter. And essentially, this results in strong gravitational perturbations that destabilize the co-orbitals. So now this leads into my research question, which was can it figure out whether or not a system's resonance influences long-term co-orbital stability, and sort of understand the relationship between resonances and stability? In order to answer my research question, I first acquired initial conditions from NASA's Exoplanet archive, and I did this so that I would be able to simulate 20 hypothetical co-orbitals for each exoplanet using rebound. So I took 5 extrasolar multi-planet systems and I added 20 particles for each exoplanet, and I modeled that using rebound. I separated the 20 particles starting first at the planet semi-major axis, and then I increased that by 1 Hill radius, which is found by this equation here. Then I plotted the eccentricity, inclination, and difference in mean longitude of the systems. And in order to sort of assess the stability, I made lifetime plots, which I will talk a little bit more about here. So in order to assess the stability, I first had to find the threshold, which was just the smallest difference in mean longitude able to remain stable. And I found this by multiplying the Hill radius by 5, which was defined by my mentor, Mattia, in a previous paper as the mutual Hill radius limit for stability. And then I made these lifetime plots, which had the semi-major axis on the x-axis and the lifetime on the y-axis. And I found this lifetime by taking the stability time and dividing that by the period of the host planet. And then in order to visualize the instability on these plots, I added horizontal lines that served as indicators, and I plotted these lines by taking the total simulation time and dividing that by the host's period. So now these are the multi-planet systems that I modeled. I started with TRAPPIST-1, which is in 2-body resonances. I went to Kepler-11, not in resonances, Kepler-80, which has 3-body resonances, which are weaker than 2-body resonances, Kepler-90, not in resonance, and HD 110067, which is in 2-body resonances. So now a little bit of my findings. These are subplots which have the total simulation time on the x-axis and the difference in mean longitude on the y-axis. So the mean longitude of the particle minus that of the host planet. And this is specifically for TRAPPIST-1b, which was over 10 to the 6 years. And now these patterns here, these are representing stable Trojans for the entire duration of the simulation. Here we have particles that were initially stable horseshoes, but they died off. And down here you see no patterns, and this is due to the fact that there were no stable particles. And now here I have Kepler-90f, which is not in resonances, and this is over 10 to the 5 years. So we see a lot of differences in the patterns. So here we have a particle that's alternating between a Trojan and a horseshoe. We have a particle that starts as a horseshoe and then switches to a Trojan. Here we have stable horseshoes for the entire duration of the simulation, and we also have multiple stable Trojans. So just looking at this planet's co-orbitals as opposed to TRAPPIST-1b, which was in 2-body resonances, there's a lot more stability surrounding these particles in this system. And now I have my lifetime plots here just for 3 of these systems. So we have TRAPPIST-1, we have Kepler-80 and Kepler-90. And the way this plot is the way that this plot was created was we have the stability indicators, which are dashed lines, and they correlate to their respective colored points, and the points represent the 20 co-orbitals of that host. And so if a point is along the dashed line, that represents a stable particle, but if the points fall below the respective lines, that means that they were no longer stable. And just looking from the 2-body to the 3-body to the non-resonant system, you see that the particles in the non-resonant systems are able to remain stable as opposed to TRAPPIST-1, which has the blue, you see the blue dots are kind of start out as stable, but as the particles increase in their Hill radius, they fall off. And so you can see that the resonances have a great effect on the stability. And co-orbitals are less stable in resonant systems, with Trojans generally being more stable than horseshoes. But what is the relation? Why is it that resonance is able to affect the stability? And this is due to the fact that co-orbitals of one planet are also in or near resonant with other planets, and this potentially causes dynamical chaos. And also, the stability is linked to dynamical interactions and resonances within the systems. And this is important because if we're able to enhance or expand our knowledge of co-orbitals, this could inform future observational strategies for their detection in extrasolar planetary systems. And that is all. Thank you to SETI Institute, Vassar, NSF, DPS Travel Grants, and Zaria, my cat. And I have my GitHub repo here, and here's a QR code to my website if anyone is interested. Thank you so very much.
Awesome. Thanks so much, Mariah. One of the things I like the best about the DPS is that you can hear talks about Trojans now, around every planet in the solar system, around the exo stuff. I'll invite all the speakers to turn their cameras back on. We're going to start doing the Q&A, right? Where we're going to go in order. And I'll remind for the people watching online that you can ask questions in the Q&A section of the chat. And I have a few prepared just as people are getting started. So my first question is for Amy Simon and her group. Obviously, I love images of the Great Red Spot. I think everyone does. I think it was really cool. And I love the fact that, you can see so many different changes happening on the same timescale. I was wondering, do you have a sense of what sets that 90-day timescale? Sorry, I'll get there in 1 second. What sets that 90-day timescale? And as the Great Red Spot continues to change, whether or not it will retain that same timescale. So all right, here we go.
Yeah, that's actually a really interesting question. We don't know what sets the 90-day timescale. There's, of course, lots of guesses, but we really don't know. And what's even more interesting is we see that 90-day timescale on Neptune as well, which is a smaller planet. So there's some fundamental characteristic of the rotation and deep structure of these planets at setting that 90 days. We were certainly interested as the Great Red Spot continues to shrink, will we start to see it sloshing around like we saw in those great dark spots, because right now it's very much constrained by the wind field. And if it gets smaller, it may not be. So it is something we'd like to sort of track more in the future, as well as we'd like to do general circulation modeling to see if we can replicate not just a 90-day cycle, but all these other things oscillating at the same time, sort of seeing the Great Red Spot breathe in and out, which really was a little bit unexpected.
Awesome. Thanks so much. Another question just popped up for you in the chat, but we'll come back to you in a second. Question for Richard. When people think about the Uranian satellites, people often will compare one against the other, together. One of the questions people always ask is, as you get closer to Uranus, you're close to the magnetic field, all this other environment, in what ways do the new results you have sort of fit into that framework? Or with this new era of high quality JWST data, are more puzzles even popping out, the closer you get a chance to look?
I think your question is about the irradiation environment. Yeah. That's a great point. Which is why we can't and won't rule out the irradiation hypothesis. It's certainly still in play. The uranium moons continue to show the same leading trailing asymmetry in the distribution of CO2 that we saw from ground-based data that we used to think or still think is from charged particles primarily hitting their trailing sides and forming CO2 molecules in situ which then build up over time. It's just with the better quality, the higher signal JWST data, there's these additional wrinkles which are starting to come into the picture, like the absence of hydrogen peroxide, which was kind of surprising, that are adding to the mix. There's also more going on in the moon magnetosphere interaction literature and in that world, and the models that are starting to come about soon to be published suggest that the interactions might be fairly low with Ariel.
Great. Thanks so much. Question for Mariah, for your, systems, you were talking about how, if we're able to figure out which systems might be, better suited to hosting these long-term Trojans and co-orbitals and horseshoes and all that stuff, we might, get better at thinking about ways to detect them in the future, or at least sort of identify which places they might be. Have you thought about how you actually might go about detecting these kind of things, or maybe if not explicitly detecting, at least sort of getting a hint that they might be there?
Great question. So I am not at all an observational, well, I'm not I'm not really specializing in anything just yet because I'm still an undergrad. But my project was heavily theoretical, but I can say it can be implied that sort of if you know the sort of dynamics of a system and how their resonances sort of, if you're familiar with how a system's resonances sort of affect the planets themselves, I think that you can be more inclined to know where co-orbitals might be and where they probably are not able to be or are not able to remain. So I think knowing the sort of dynamics of the system can help in leading to knowing where to point, if that makes sense. So it's kind of I guess you would have to know a little more about the system itself, but once you know a little bit more about the system, I think knowing how co-orbitals are able to navigate and how co-orbitals sort of live, for lack of a better term, in systems can help you in knowing whether or not to look for them in that particular system. Does that answer your question at all? That was kind of a roundabout way of.
No, I'm an observer by training, so I figured I was going to for questions. So
Yeah.
I think that's cool. We have a question for Amy, which I'll sort of summarize a little bit. When you say that the Great Red Spot drifts over time, does that mean that the storm, makes its own circuit around the planet, plowing through other stuff going on in the atmosphere, or?
Yeah, that's a good question. And that's pretty much absolutely what it's doing. So these large storms don't move with the wind field. It's the small clouds that we use to measure what the winds are doing. And instead they're rotating and they're kind of rolling along, but they also move at their own little rate, which doesn't match the surrounding wind. So it actually takes a few years for the Great Red Spot to go all the way around the planet, but it's doing it at its own rate.
That's really interesting. Back to Richard then. I gave you the hard question first about the irradiation environment, so I'll be a little bit nicer this time. You were talking about how some of this stuff, like the potential carbonates, right, might have been sourced from the deep interior. You're getting spectra of the whole moon all at once, right? So you might not know exactly which spot the carbonates are coming out or the connection is being made, but based on the limited images that we do have, do you have a sense on which places on these moons or on Ariel specifically are where that connection is taking place or had taken place at some time?
Yeah, not really. So because of the timing of the Voyager 2 flyby, the equator of Ariel is right at the terminator. And so some of the most interesting geology is right at the edge of what we can actually see. And so there looks to be a set of chasmata that straddle at least Ariel's trailing hemisphere at low latitudes close to the equator. We don't know about the leading hemisphere because the imagery of its leading hemisphere are really garbage. So we can't see anything. We just don't know what's in those data. So we have a small sample. And so we're trying to work with it as best as we can. So I will say in a speculative fashion that I would expect it to be associated with younger geologic features using Ceres as the analogy, where we have the bright carbonate salt deposits in Ockerter crater, which we think originated in its interior, which formed in the past and when the rock was in contact with some water and then got expressed to the surface through one mechanism or another.
Right on. Mariah, question for you then. When it comes to, finding, you studied these 5 different systems and you looked at which ones had stable co-orbitals, stable horseshoes, all that stuff. Given the results that you have here and you've presented at our cool meeting, do you have a sense of which systems in the future might have, sort of the ideal setup or sort of the right conditions to have tons and tons of these objects, setting aside whether or not they actually, have the Trojans, have the co-orbitals, which, it seems like every planet in our solar system has a slightly different story to tell there.
Yeah, so I would say my findings sort of highlighted that the most ideal environments for these co-orbitals would be systems that are not in resonances. And so I think kind of I guess that is the short answer to your question, actually, now that I think about it. Yeah, so just systems that are not in resonances or systems, because whenever we looked at the three-body resonance ones, systems that have weaker resonances, just kind of so the gravitational perturbations are at a minimum.
Sure. So the systems like TRAPPIST-1, which have all these perfect ratios between their orbital periods, even though they're really interesting and cool for other reasons, they're not really perfect setups for what you're interested in.
Correct, yes, which is sad but true.
Awesome, thanks. I think we have time for at least one more question per person, but I'll go to Amy next. So the Great Red Spot is the best studied storm on Jupiter, right? I say that not knowing it's true, but I assume it has to be, right? What kinds of insights can your study give us to how other storms, other atmospheric effects are going on Jupiter? Or is the Great Red Spot kind of, unique and special in its own way that makes it kind of hard to translate elsewhere?
Yeah, that's an excellent question. So the Great Red Spot is a high pressure system, which is a little different for us here on Earth, where we're not used to these big storms being high pressure systems. But most of what we call anticyclones, so opposite of cyclones, are high pressure systems. They're all very rounded. The Great Red Spot's clearly the biggest. It's clearly been there the longest, as far as we know. And it's gotten the most study, in part because it is so big. So we can use something like Hubble and get really good resolution in its interior. Something like James Webb, spectacular results about the Great Red Spot. It's much harder on the other storms. So the other storms are obeying the same physics, but they're a little bit harder to observe. So from that perspective, being able to understand more about the Great Red Spot will help us study them, but we don't know enough yet. So they may be much more shallow systems. So I think the more we learn, the more questions we're going to have, and the more we're going to ask for time on these big telescopes to look at them.
As it should be. I have one small follow-up question based on a question that we got in the chat, which is, you'd mentioned earlier that the Great Red Spot, has this 90-day period, and Neptune has something similar going on, and you said you weren't entirely sure why these two systems had the same timescale, right? Does your study or a future idea you might have give you any way that you might be able to attack that problem and understand why 90 days seems to show up at least twice?
Yeah, that's a good point. And this is going to come down in some ways to circulation modeling, which a lot of my colleagues work on in great depth. And now that we have some parameters where we've got all these simultaneous measurements, these are all different parameters we can feed into our circulation models, because we know what the answer should be, but there's a lot of unknowns. And so now we can constrain more of those areas at the same time. And if a model can uniquely, which is always the trick, if it can uniquely constrain deeper structure or motions below the clouds that we can't see, then we'll have really learned something. And so that's part of the impetus behind observational studies, is to then be able to feed it into the parts that we can't yet see. Great,
thanks. Richard, I want to ask you the default conference question, which I think is boring in some context, but I think is exciting here, which is, what's next for the research, right? Even if we were all to sign off and get the Uranus orbiter approved tomorrow, it's going to take a long time, and there's going to be time to ask new questions. What's next? Is it more JWST data? Is it more modeling? What's up?
Yeah, it's always more data. Because of seasonal change in the Uranus system, the spectral properties of the uranium winds are changing in subtle but important ways. And so as the subsolar latitude is changing, we want to continue to observe them. And this is also, it's not just science for the sake of science in the moment. There's also a historical context here, because when UOP does get to the system at 2050 or slightly later than that, we're going to have lost the northern poles, which we're able to see right now, or at least we'll have lost most of them from in terms of characterizing their spectral signatures. So we built that data set up now. We'll have that for when the mission gets there, and we can compare and contrast and do all that fun stuff.
Awesome, thanks. All right, so for the last question, I'm going to ask Mariah a little bit of a tough one. When we're looking at exoplanet systems, we're getting better at finding exoplanets all the time, right? But it's easier to find certain kinds of exoplanets compared to others, right? The really far away and distant ones, which might have long periods, maybe they don't transit that often, they could be in some of these systems and we just can't find them yet. We might only have hints. For the systems you studied, or in general, if there were more planets sort of waiting in the wings, would that make the situation of keeping, Trojans and Horseshoe co-orbitals around tougher, or are there situations where maybe it wouldn't matter so much?
That is a very, very interesting question, and something that I have not thought of before. So I'll talk about what I do know, and maybe from there we can imply some things. But so I know for Kepler 90 specifically, if I'm but correct me if I'm wrong, I'm pretty sure that is a system with the same number of planets as our own solar system. However, the farthest planet is, I think, at around 1 AU, so they're pretty close together and crowded in comparison. So I'm not certain if the this is very, I'm not sure if I am able to answer that question accurately. I can say that I don't know. We haven't really explored the number of planets in a system and if the number of planets will affect the stability or presence of co-orbitals. More so just the sort of resonance aspect of things. So, I mean, it's very possible that there being additional bodies could affect these, but that is an avenue that we unfortunately didn't discover or we didn't look at. So I can't accurately answer that, but that was a very, very thought-provoking question. I appreciate it.
Well, I've never asked a question that people have thanked me for quite like that, so thanks. Before we close out, I'd like to thank all of our speakers again. I think you all did fabulously. And I think I'd like to remind everyone watching online now and later, this is a subset of all the cool work the DPS is doing, right? This is one of the few press conferences where you can go learn about, atmospheric dynamics on Jupiter, the surfaces of the Uranian moons and exoplanets all at the same time. And we're all kind of speaking the same language, right? It's a unique environment and it's really important and I think exciting that all of you got to experience this either now, today, or when you're watching it later this week, catching up on work. I'll thank again my colleagues from the AAS, Susanna and Carrie, as always, for doing all the work to help these DPS meetings or the DPS press conferences get set up behind the scenes. And, thanks to all of you for watching. Again, whenever you're doing it, it matters. We do a lot of cool science around here, and the only way that the public gets to hear about it in most cases is when journalists take that interest. So thank you so much. And with that, I'll say that's the end of the press conference, and we'll see you again next year, where DPS is in Helsinki, amazingly. So I will be loving that part, of course. But yeah,